Hi, our team developed a KV storage system for parallel architecture for the final project. Here's our presentation. KV storage is widely used in algorithms and services with low time complexity for putting and searching objects. Most implementations does not support concurrent operations. Besides, storage space on a single node and contentions are still problems. That's why we decided to design and implement a KV storage running on multiple nodes to support parallel algorithms. We use MPI to perform communication. We designed our protocol based on optimistic asynchronous models, but find that message passing layers are filled quickly. Therefore, we modified it by adding a synchronization. Specifically, after sending a batch of requests, the master will wait for these requests to be received. These seem like a combination of optimistic and conservative asynchronous models. We also compare different architectures. A peer mode is where each node can receive requests and forward requests, but it has a probability of deadlock because nodes may wait for each other. Finally, we implemented a master worker model where masters dispatch the requests based on a very simple two-level hashing quickly, and workers execute the particular operations on the hash table.
We have tested or benchmarked based on the following rationales. The serial case represents there are many master nodes sending requests to one single worker node. The parallel case applies as we deploy many worker nodes to accept the request to do the value lookup and store. In the BSGS case, we simulate the real-world situation when the parallel KV store is used. In the serial worker case, there is only one worker node dealing with requests sent from multiple master nodes. As the master nodes increase, it takes linearly more time to complete the calculation. In the parallel case, we have multiple worker nodes to accept requests in a distributive way. As we could observe from the graph, when there is one master node sending the request, the speedup is not very obvious. But when the master nodes are set to 4, we could observe the speedup goes up along with the number of worker nodes in the first half. Then the speedup decreases. It is because the worker nodes resource grows redundant, and more worker nodes imposes the extra overhead at synchronization. While the testing against the real-world case, we deployed the BSGS algorithm upon generating the trace. The test result indicates 10 times speedup compared with the serial counterpart. The speedup comes from 8 master nodes and also from more workers that are hired processing the requests. For limitation of our work, first, we did not consider the overhead between callers and masters. In fact, this overhead is inevitable because such trace doesn't exist in reality. Besides, our system cannot do dynamic scaling while the workload could change while functioning in reality.